Okay, in the third electrolysis section, we look at production of useful chemicals by electrolysis. Now, lots of chemicals are produced this way, and this is the same as with electrochemical cells. We don't need to memorise particular examples of cells. We just need to understand how the principles of electrolysis are reflected in the design of a particular cell. Now, electrolysis is only used where we can't produce metals chemically, because electrical energy is expensive, so it's basically the last resort. And these are expensive energy dependent applications, so if it's to be viable, we need cheap electrical power. So the big electrolysis industries go to countries in the world where there is cheap electrical power. That used to be the case in Australia. So 50 years ago they were building aluminium smelters. Now it's most definitely not, so they're closing all the aluminium smelters down and going elsewhere in the world. Cheap electrolytes. So if you can engineer your electrolyte to be cheaper and still work well. Cheap electrodes. You quite often consume large amounts of electrodes. Continuous production too. If you want large amounts of chemicals to be produced, you need to have a cell that continuously produces chemicals, so it continually has reactants being added in, and operates at as low a possible temperature. High temperatures require lots of energy. Energy is expensive. So if you can get the operating temperature down as low as possible, you're going to save lots of money. So let's look at a few examples. First of all, the Downs cell. Molten sodium chloride. It's the example that we looked at in theory before. And this is the way that sodium metal gets produced. It produces chlorine gas as well, but as you'll see, chlorine gas can be produced more cheaply other ways. So what have we got? We have got a graphite anode. So the anode's made out of graphite. So that's resistant to temperature. Graphite is stable at high temperature. And that's where the chloride ions are going to be oxidised to chlorine gas. Now, that is separated from a couple of iron cathodes. Now, the iron cathodes are where sodium ions are reduced to sodium metal. That sodium metal has low density, it floats up and gets pumped out as a liquid. The chlorine gas at the anode, of course, is a gas, so it just bubbles through and is collected as a gas. Constant fresh supply of electrolyte. Now, in electrolytic cells, we need to keep the products separate from each other. So we've got an iron mesh screen designed to keep the sodium metal and the chlorine gas separate from each other. Because in an electrolytic cell, it's the products which are going to spontaneously react with each other. And believe me, a fair amount of molten sodium coming in contact with a reasonable amount of chlorine gas, it would be a spectacular thing to see. There wouldn't be much left of your factory afterwards. Now, the electrolyte is a mixture of sodium chloride and calcium chloride at 600 degrees. Why is calcium chloride included? Well, to reduce temperature. Sodium chloride melts at 850 degrees, but by adding some calcium chloride as well, having I think it's a 1/3, 2/3 mix, you reduce the melting temperature to 600 degrees. That lowering of 200 degrees reduces the cost of the process enormously. So that's designing the electrolyte to reduce temperature and reduce cost. We also see we've got iron cathodes because they're good, strong, cheap, and if they're the cathode, they're not going to react. So they're an inert electrode at the cathode. But if you were to make the anode out of iron, what would happen? Well, iron, of course, is a strong reducing agent, so it would react straight away. You wouldn't have an anode for very long. So you can't use iron at the anode, so you use graphite instead. So the reactions are pretty simple. We've got the sodium ions being reduced to sodium metal. At the cathode, we've got chloride ions being oxidised to chlorine gas at the anode, and those features that I mentioned just before. Now these are massive industrial operations. 40 cells, 30,000 amps, each cell's 7 volts. So huge amounts of electrical energy and huge amounts of chemicals being involved. As I say, the electrolyte was that mix of sodium and calcium chloride to reduce the cost, the operating temperature. The temperatures maintained, these electrolytes have a significant internal resistance to them. So it's the potential drop, it's the voltage loss across the electrolyte that generates lots of waste heat, and that waste heat's not actually waste heat, it's the energy required to maintain the 600 degrees. So I've set some Faraday's law question based on this cell. So do those now, just a few little hints. It's over a 24-hour period. You need to work out how many seconds there are in 24 hours. Now if you do your calculations, you should get 16.5 tonnes. If you get somewhere around 0.5 of a tonne, just remember you've got 32 cells. You've just worked out how much chemical is produced in one cell by doing the calculation the normal way. You're going to have to times it by 32. Likewise, when you work out the energy, you're going to have to calculate it based on 7.2 amps being dropped over 32 cells. Now we look at the membrane cell, which is how the bulk of the chlorine gas actually gets produced. So the down cell operating at 850 degrees is quite an expensive way of producing chlorine. You can actually get chlorine gas out of electrolysis of aqueous sodium chloride. So if we look at 1 mole of sodium chloride, as I think we did before, we see that at the cathode we get water being reduced. That's pretty straightforward. We get hydroxide ions produced. That gives us sodium hydroxide, of course. At the anode, things are a little bit more complicated. If we've got 1 molar sodium chloride, then we've got standard conditions. The stronger reducing agent is water. Water preferentially gets oxidised. However, they're reasonably similar ENOT values, and the voltages depend on the concentration, and in this case, which reaction occurs also depends on the concentration. So in dilute solutions, water is what gets oxidised. However, in concentrated solutions, the higher the concentration, the chlorine reaction begins to take over. By the time you get to a concentrated solution of sodium chloride, it's pretty much just chlorine gas which is being produced. So we get to the membrane cell. So we've got aqueous sodium chloride in this case. Now we've got, similar to the molten electrolyte version, the down cell, we've got a steel cathode with a mesh to give it a high surface area. Steel is good and conductive and cheap and strong. However, our anode has to be made of graphite because you can't have steel or else it'll be oxidized again. So we've got chlorine gas being produced at the anode, it gets taken off, and we've got hydroxide and hydrogen gas being produced at the cathode. Again, it's the products which need to be kept apart. So the hydrogen gas and the chlorine gas have to be kept apart, and that's one of the functions of the semi-permeable membrane. So it allows ions to flow to complete the circuit, like in a salt bridge, but it keeps the products separated. So it's a cation permeable membrane, only allows the sodium ions to pass, not the chloride ions, not the hydroxide ions. So this has the happy result of not only keeping the products apart, it also means that the chloride ions don't flow into the cathode chamber. So the hydroxide that you get is pretty much pure sodium hydroxide. And they're the points that I just made. So we've seen a couple of structures so far which are designed to prevent spontaneous redox reactions by keeping products apart. So the membrane or the steel mesh in the down cell keep the products apart because they are what would react spontaneously. In an electrochemical cell, of course, it was the salt bridge or the membrane barrier in a galvanic cell in a battery that keeps the reactants separate, because in an electrochemical cell it's the reactants which would react spontaneously. Both allow the electrolyte to pass to complete the circuit. Production of aluminium, very useful metal, also very reactive. Chemically, it's exceedingly difficult to produce. So it was one of the most expensive metals in the middle of the 19th century before electrolysis was developed. It's only the development of this process which has made it the ubiquitous metal that we have today. Now, it is very reactive, so why doesn't it just react? Well, one of the fantastic properties of aluminium is that when it oxidizes, the thin aluminium oxide coating that forms on the surface actually is a really solid coating. It doesn't allow the oxygen to pass through, so it protects the underlying metal from further oxidation. You compare this to iron. Iron oxide's really flaky. It doesn't do anything to stop the oxygen getting through, so the whole lump of a piece of steel, piece of iron, can oxidize, and the iron oxide just flakes off. Aluminium oxide, that's not the case. We can improve on that coating. We can make that aluminium oxide coating thicker by a process called anodizing. Now guess what? That involves making the aluminium object into the anode and producing a thicker oxide coating on the surface. It's also when you can chuck in a little bit of dye to get nice brightly coloured aluminium objects. So the aluminium cell or Varroa cell Again, we've got a carbon cathode. So in the case of the aluminium cell, you've got even higher temperatures. So an iron cathode would just not be strong enough. So graphite is more temperature resistant. So you make your cathode out of carbon. You've got the anodes made out of carbon as well. And we'll see that's very important in a second. You've got your aluminium oxide being constantly added to the electrolyte, and it melts. It doesn't actually melt on its own. It's actually mixed with another ionic substance called cryolite. It's a mineral with a much lower melting point. So that's less dense than the molten aluminium, which is formed at the cathode, sinks to the bottom and then gets pumped out, and the product of the anode is actually carbon dioxide, as we'll see, and that gets taken out the top. So the cryolite, which is actually sodium aluminium fluoride, takes over 1,000 degrees off the operating temperature. Huge energy savings, makes it an economic process, which it wouldn't have been otherwise. So that's the solvent. We dissolve the aluminium oxide in that. So if we're tempted to write states for these equations in this cell, we need to say in cryolite. That is, it's not liquid, definitely not aqueous, it's in cryolite. Cheap and conductive, reasonably cheap and conductive, stronger and more durable than iron. And it's very important to reduce energy costs as well. So there's a two-step reaction at the anode. You get oxide ions, and the state of course is in cryolite. Oxide ions being oxidised to oxygen gas. Now, as soon as the oxygen gas is formed, it forms on the surface of the anode and it oxidises the carbon there. At around about 1,000 degrees, that's a fairly easy reaction to occur. So basically, your oxide ions are reacting with carbon to produce carbon dioxide. Now, this massively reduces the voltage that's needed and therefore saves huge amounts of energy. The cathode reaction is pretty basic. Aluminium ions being reduced to aluminium metal, sinks to the bottom, as I say, and gets pumped out. So we can combine those equations into an overall equation. And we see our carbon anodes are being consumed. That's obviously cheaper to keep on replacing your carbon anode than it is to have a much higher voltage. The last of the electrolytic processes that we look at is a very neat way of purifying copper. So when copper is being produced from copper ores, the first step is a chemical smelting process which produces an impure blister copper, 98% pure, and that is just not good enough to for most applications. So we've got to get rid of those impurities, which are elements such as those listed there. Some non-metals, some reactive metals, some less reactive metals. So what we use is an electrolytic process, and that gets it to, as it says, 99.9% pure. So basically, we put the blister copper sheets, the impure copper at the anode, and we oxidise them. So that produces copper ions, and then the copper ions turn back into copper metal at the cathode, and by very carefully adjusting the voltage, we get lovely pure copper produced. So carefully adjust the voltage, just enough to oxidise copper. Therefore, any more reactive metals than copper will be oxidized as well. So iron, zinc, both metals below copper in the electrochemical series, them and any other metals below copper will just be oxidized, move into solution. All the metals that are less reactive than copper, such as gold and silver, they will just fall off. As your copper anode oxidizes, the less reactive impurities won't be oxidized, they'll just fall off the electrode, fall to the bottom of the cell. So it'll produce mud, a rather valuable mud, and then the copper ions and any other ions in the electrolyte can move over to the cathode. What happens at the cathode? Well, the voltage is just enough to reduce copper ions to copper metal. Any of the more reactive metals that formed ions, well, their ions are going to be less reactive ions, so they will not be reduced. Only copper ions will be reduced to form pure copper metal. All the other ions of more reactive metals will simply remain in solution. So that's the end of electrolysis. Submit these questions on Google Classroom and I'll get back to you with the solutions.